just to reinforce with you, we have our final exam 2 Saturdays from now. I want you to double check your exam schedule. Saturday afternoon and Saturday evening are supposed to be free time in exam week. They call it the free period. And so you may have a conflict with one of your other professors. With another final. If that's the case, have your instructor get in touch with me. A conflict, yeah, see you guys later. A conflict does not mean tailgating before the game or anything like that. Conflict means you have another final Saturday afternoon. If that's the case, then we'll get it ironed out. Your instructor should contact me, and then we'll work out some plan for that. Okay, here's our best, our outline. Yeah, see you guys later. Whoever else wants to leave, we're not doing any clicking. I forgot my clicking equipment. We can't do any clicking. If you want to leave, go ahead. All right. Best 2 out of 3 is up. I still have SSG bonus points to do. I have homework to round up. I have clicking to round up. A couple things I want to point out to you. In the grades page, it'll look something like this. For this hypothetical student, there's the exam 1 grade, which is right here, 45 out of 50. So you could jot this down if you want as an example. So 45 goes down on your scratch paper. Then we've got exam 2, total of 41 out of 50. So that goes down on your scratch paper. And then you've got exam 3, 42 out of 50. So that goes down on your scratch paper. Now, all those three, if we were going to take an average of your 3 grades, the average would be 85.3. But what we do is we cancel out, so put an X through the let me get my cursor. Put an X through the 41. That's the one that we drop. Now, I've done that for all of you. All of you that have 3 exam scores. Now, if you've been absent for one of the exams, exam 1, 2, or 3, you have a 0 or maybe a -1. And that means I took your only 2 exam scores. And that is in the best 2 out of 3. Now, that's only for a few dozen people in both sections out of 600-something students. So most of you have got 3. And the nice thing about that is instead of having an average of 85.3, when you take the best 2 out of 3, you have a little bit better grade. If you have 3 different scores, okay, if you have all the same score, then dropping one of them is not going to help. If you have 2 of the same score, so if you have a 45, a 42, and a 42, well, we're going to drop one of the 42s. And actually, yeah, that will improve your score too. So that would be an 87% as well. Usually, doing best 2 out of 3 is a nice little bonus. Well, it's not bonus points, but it's beneficial for your exam or for your semester grade. I had some really bad, the reason I'm having a bad day is because I had some really bad news about my son. I'm extremely worried about him. Sorry. Let's keep going. Special study group leaders. I want you to get your time and date figured out. It can be completely different location, time, and it'll be a different day. I want you to get that to me as soon as you can. The rest of you guys will try to put together the schedule page and have it all ready by Thursday, 7 p.m. signups. So the Buffalo Stampede will begin at 7 o'clock Thursday night, hopefully, if we can get all the schedule items up on the page. So it'll be kind of like last time. Questions about that? Yes. The question was, do you want me to email that to you? No, do not email me, but do use the messaging system in web courses. You don't have to print out that page again and sign it or anything, but just a course mail message will suffice. Unless you've already got it written down with you now, you can turn it in now. Okay, study union, as I've mentioned before, that's going to be next Monday. Study day from 1 to 3 in the Pegasus Ballroom. And the normal procedure for SI is always you go, if you can only make the last half hour, I mean, you got another study group for anatomy or something, and you can only make the last half hour, go for the last half hour. That'll help. If you can only make an hour from 1:30 to 2:30, go. If you can only make the first 45 minutes, go. And then sneak out at the 45-minute mark. That's good. Just get there. And I'm going to be having office hours on Wednesday, mega office hours over in physical science. So hopefully we'll be able to get in a lot of study. Plus you'll have SI and get yourselves ready for the final exam. And the final exam is about 2/3. I've figured out about 2/3 of it now. So it's going to be comprehensive, and because it's going to be comprehensive, it's going to be difficult. Even if I put all easy questions on it, because the questions go all the way back to August, and it's two more days will be in December, that's a long way back to remember fine points. So that alone, even if I make all the questions easy, it's going to feel hard because it's a long way back to remember. So be very serious about preparing. I don't give finals that are cinchy. It's going to be challenging. Okay, so be loaded for bear, as they say, and hopefully you'll be able to get a good grade. You may remember this image from Lord of the Rings, Grond, the big battering ram. That phrase there, "Opignat molibus urbem," I looked that up on the internet. That's a Latin phrase, and we're actually going to be talking about molibus. The root word for that is moles in Latin, and it's related to the word molecule and mole that we're going to talk about for a few minutes. In Latin, moles is the root word for a shapeless mass or a huge bulk. And that's what they've got in this picture. Who are the orcs? The orcs from Mordor were bringing this big shapeless bulk. Opignat, you know what that means literally in Latin? It means attacks huge bulk on the city. Urbum, city. Opignat, pugnacious. Have you ever heard that word pugnacious? That means fisticuffs. Okay, so they're trying to drive a fist into the city, a huge one. And so the molibus, M-O-L-E-S, means a huge bulk. Cule, the suffix, denotes smallness or, a fraction. And you can look that up at dictionary.com and other places. And so a molecule is a small part of a shapeless bulk. Now you may think, Dr. B, what's shapeless bulk? I mean, that's like, some kind of superhero movie or something like that. The Incredible Hulk, the shapeless bulk. No, what it means is that, you have this huge mass. For instance, the atmosphere. We know that there's an atmosphere. We can see the blue color on a sunny day, but we can't actually see the atoms, the nitrogen and the oxygen atoms in the atmosphere. We believe that they are there. We've actually measured. We are now fairly confident, very confident, that molecules are there. But they make, the atmosphere is this whirling, boiling, seething mass of indeterminate shape, roughly spherical, and coats the Earth. But it's definitely not smooth. It's not a perfect sphere. So you could call it this big shapeless bulk. Here's a picture of a molecule, NH3, ammonia. The blue circle, the blue sphere there is meant to symbolize nitrogen, a nitrogen atom. The white spheres are meant to symbolize hydrogen atoms. And the two little dots up there are actually non-binding electrons that are repelled over to the top end of the ammonia molecule by the bonding process. And we'll talk a little bit more about that in a few minutes. Anyway, that's an example of a molecule. Atomic mass unit, you can read about it on page 230. This is the typical atomic mass unit. You don't use kilograms to measure. Well, you can. I mean, you can rate the mass of a proton or an atom or a molecule in kilograms, but usually you use the atomic mass unit. And by agreement, we've set it to be exactly 1/12 of the carbon-12 mass. So we measure whatever carbon-12 is, and then we say, all right, 1/12 of that is the official AMU. Initially, in the 1800s, some people wanted to go with hydrogen as the atomic mass unit, and hydrogen being equal to 1, and then everything else is a number larger than 1. And then, Chelsea, some people said, well, no, let's use oxygen, because oxygen is easier to work with, and you can oxidize with it. Excuse me. And so oxygen, that's 16. And so some people say, well, let's use oxygen, and but now in the past, I don't know, 80 years or so, they've decided that we'll use the carbon atom, the carbon nucleus for that. Now I want you to look at this little fragment, this little tile from the periodic table, and bearing in mind what we were just talking about, the atomic mass unit, is there anything in there that looks a little bit what do you call that? A kilter. Is that a word? Is that how you say that? Yeah. Something a little bit askew. Is anything in there? You see something? Hold on. Anybody else see anything? Look at it carefully. Is there something that's not quite right? Don't look at me. Look at the... What do you see? Think. What do you see? Did you see? Did you? Oh. Is it moving? No, it's not. No, that's maybe your eye. No, it's not moving. No. This is moving. What do you notice in there? Carbon. You know the atomic number 6. 6 protons in the nucleus. 6 electrons in the neutral atom. Sarah. Repeat. Yeah, it's not exactly 12. What is this? How come it's not exactly 12? Is that what you were thinking? Yeah. Why is that? Okay, the atomic mass unit, that should be exactly 12, right? Carbon. But it turns out that there are several variations in nature of the carbon nucleus. They're known as the isotopes of carbon. Here they are. The first one, and the most abundant in nature, is the carbon-12 nucleus. All right. And it's represented, you can represent it this, you can say the word carbon-12, or, which I've got up here above the image. And then down below, C12 with a 12 upstairs like an exponent, only it's in front of the symbol. Or you can write it in full isotopic notation with the 6 downstairs and in front of the symbol. And that tells you 6 protons and 12 nucleons, 12 items in the nucleus. So this, again, is one way you can say, well, all right, 6 minus 12 is 6, so I have 6 neutrons and 6 protons. Okay. Now, a variation of the carbon, some of the carbon in the universe, way less than 1%, is carbon-13. And another rare form of carbon nucleus is carbon-14. Carbon-13 is manufactured spontaneously in the well, I shouldn't say spontaneously, in the upper atmosphere when cosmic rays, which are ultra high-speed particles, flowing around in space. We don't know where they come from. Well, they come from stars and stuff, supernova explosions, I guess. And they're floating around. They're flying around in space. They crash into particles in our atmosphere, in the gases in our atmosphere. They form carbon-13, and then you breathe it in, and it becomes part of your body. So some of the carbons in your body are carbon-13s. The other way that we can make these is inside of a nuclear reactor where there's zillions of neutrons to work with. But anyways, in the atmosphere, a lot of carbon-13. That gets into your digestion and you breathe it in. Plants, when they take in carbon dioxide, some of that, almost all of it's carbon-12, but some of it's carbon-13 until the tree is cut down and burned in the campfire or whatever happens to it. Once that happens, it no longer takes in carbon. And so the carbon-13, it's unstable, it's radioactive, it's not very dangerous, but it's unstable and it will decay at a certain rate. And with that, we can do chemical analysis of a piece of wood or a piece of bone or something like that. And from a campfire in some cave that the cavemen used 12,000 years ago, we can figure out how old that campfire was. And that's how we know, how old all kinds of different archaeological specimens are. So that's carbon-13. Anyways, this is the most abundant carbon in nature. These two are rare. It's not hellaciously rare, but it's definitely a very, very small proportion of the carbon in the universe. So that's why that number is 12.011. And so what the number in the periodic table really tells you the average in nature. So in nature, 12.011 tells you that you have mostly 12s, and you have a few 13s and 14s, but not enough to budget up to 12.5. But it does budget away from 12.00. Or another way to put it, if all the carbon was only 12, carbon-12, then that number would be 12.00 flat. But we got a little bit of heavy carbon around, so the average is a little bit higher than that. Now, let's get back to this idea of moles and stuff. Okay, atomic mass unit, 12th of a common carbon. So what that means is for water, you've got oxygen, that's oxygen 16, 8 protons, 8 neutrons in the nucleus, 8 electrons in the neutral oxygen atom, and then 2 hydrogens, that's 1 proton, 1 electron, in the neutral hydrogen atom. So in the H2O molecule like this, you have the molecular mass is 18 AMUs. The mass of a mole, metric system mole, okay, so this is the bulk measure, is 18 grams. In other words, we set the size of the mole, the bulk measure, to be exactly the number of molecules in a shapeless bulk so that you have exactly 12 grams when you have that number of moles. And the number of molecules in a mole is 6.022 times 10 to the 23. It's a big, ginormous number. Okay? And in 1 ampere of current in your household or in your car, there's on the order of 10 to the 18 electrons per second going down the line. So this is even this is an even bigger number than the number of electrons in an ampere of current per second. So it's quite a big number. But it only works out for water to be 18 grams. Now, I don't know the real reason that they decided to use that. I guess because chemists mix up samples. They can't count molecules. But they know that elements, you go ahead and make a note of this, elements do combine in ratios. Okay, so if you know the mass or the volume and the specific ratios, in other words, like a cookbook, 2 parts flour and 1 part butter, for pie dough, or what do they call it? Crust, pie crust dough, pie crust mix. Okay, so that's, so you make as many as you want, but you keep the same proportions, if you're following a recipe. Same thing here. So chemists work in grams, so they like to keep the ratios. I think that's why they do it. Now, if chemistry ran itself on the basis of ounces, then this number would be something different from 6.022 times 10 to the 23. But in the metric system, if you want the same number of grams as your molecular mass has AMUs, then it's got to be 6.022. Now, there's some additional readings, or there's some additional items in the additional readings page inside web courses. It'll be part of your homework tonight. So when I set up homework, I'll be sorry, I've got a lot of things on my mind. Anyway, so when I set up homework, you'll have some readings to do to help you with your homework. All right, let's try an example. Silicon dioxide, SiO2, also known as silica. Let's figure out the mass of 6.02 times 10 to the 23 of those babies. Okay, so you do this by looking at first oxygen. There's 2 oxygens in SiO2, and each one of those is 15.99. Right? Then you got 1 silicon, that's 28.086 AMUs. Now that's the number of AMUs in 1 molecule. Right? So if you stack them up, 15.999 plus 15.999 plus 28.086, total 60.084 AMUs for 1 molecule in the shapeless bulk. But if you take the official metric shapeless bulk, you have to have 6.022 times 10 to the 23 of them. And so that would work out to 60.084 grams of silicon dioxide. Now that's not a very big quantity. You can hold 60 grams easily in your hand. Okay, and so that's why chemists, household quantities, a handful, a bucket, a liter. You're talking moles, or maybe a few moles, or maybe half a mole, depending on how big the container is. Okay. So 1 mole of SiO2 has a molar mass of 6.0 or 60.084 grams. All right. So underline that word molar mass. That means how many grams in 1 mole? And it's just the same number as the number of AMUs in a molecule. And that's how they've got it set up. Right? And the number 6.022 is known as Avogadro's number. And Avogadro's the guy that kind of figured all this stuff out. He said molecules exist and they combine in certain ratios. H2O is a chemical formula. And he said, you're going to have a certain number in a certain volume of whatever you have. And so in the metric system, the mole, the shapeless bulk number, based on the Latin word mole, the root word moles, is 6.022 times 10 to the 23. And that's based on using grams, the molar mass measured in grams. All right, let's get back to by the way, when I was in grad school, we had a coffee shop on campus at Montana State. And it was called Avogadro's number. I don't know why they called it that, but they had really good sandwiches and stuff. And their phone number, when you want to order, was 6.02 times 10 to the 23 or something like that. I can't remember the number now. But anyways, that was their phone number. It's kind of nice. Avogadro's, Havos. Everybody would go there and eat and study and stuff. Protein shakes. This is, strawberry, what is this? Strawberry cream, nice, very nice. A lot of healthy, nutrition facts in there, a lot of ingredients. Let's take a look at these ingredients. Let me focus in on it. Let me enlarge it a little bit. Look at that. Oh yeah, nice. Vitamin B12, okay, good, vitamins. Beta carotene, vitamin A, sea salt, Aspergillus niger, what is that? Acid stable protease from Aspergillus niger. That must be some kind of algae or something. Yeah, we got Lactobacillus acidophilus, that's good for you. Folic acid and silicon dioxide. So yeah, you might think, oh man, this protein mix, this shake mix, it's good, got vitamins and psyllium seed powder. What is so that's fiber. It's got selenium amino acid chelate. It's got all kinds. It even has silicon dioxide. Nice, right? Except the silicon dioxide, another word for it is sand. So these guys, yeah, nice smoothie. Let's put a little sand in it. It's kind of like soda pop. Coca-Cola. You look at the ingredients on that, carbonic acid. Oh yeah, let me drink a little bit of water. And just for extra specialness, let me put a little sugar in it and a little acid. Oh, not bad. Let me add some acid to my sugar water. But that's what it is. That's what gives it the fizz. I don't know. Anyways, we don't have clickers, but let's try a clicker. Let's try a question about another compound. Okay? Molar mass of CO2. Go ahead and write this down, and then choose the right answer, whatever you think is right. Go ahead and work that out. I'll give you a minute. And I'm sorry I don't have the clicker base. We've been kind of... Oh, Lord. Hold on a second. Hello? Okay. Hold on a second. I'm in the middle of lecture recording. Um, where's he going to go? If he's if he's uh, uh, if he's threatening you, you got to call the police, Joe. He's at the park. Okay. Let Joan, 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 Joan. I have to get off the phone. I'm in the middle of a lecture. All right. Let me call you back. God have mercy. All right. Sorry, Caroline. You know RJ. Very tough times. Microphone on. Okay, let's get back to work here. Sorry, I had to take a call. It's difficult. Molar mass of CO2. So it's got to be, okay, so 2 oxygens, that's about 32. And then a carbon, that's another 12, so 44. So it's got to be E, 44.009 AMUs, correct? Right? Yeah, right? Or is it, wait a minute, C? Who votes for C? Who votes for E? If you voted for E, you are incorrect. That is the mass of 1 mole, of 1 molecule. A molecule is measured in AMUs. A mole, for which you calculate the molar mass, is measured in grams. So 44.09 for a mole. 6.02 times 10 to the 23 of those CO2 molecules. Okay, now I want to talk about carbon and its orbital states. And, excuse me, we're actually going to be talking about the excuse me. I feel like Hillary Clinton. Oh. Okay. We're actually going to be talking about energy levels and angular momentum. And we talked about this last time, that the full description of the dynamical state of an electron around the atom is basically its energy level and its angular momentum states. So at the lowest energy level, so that's this inner circle here, this blue circle here, the orbital angular momentum is 0. Now, the electrons can have 2 varieties of spin. And traditionally, it's described as an up or a down spin. You can think of it as clockwise or counterclockwise for the intrinsic spin. And so the total population of electrons in n equals 2 is just 2 electrons. Okay, now every energy level is going to have a 0 angular momentum suborbit, right? Now, what is 0 angular momentum? Well, if we were thinking about the nucleus like a planet, then you could think of a zero angular momentum state as going to the North Pole and throwing a baseball straight up. It's going to come straight back down to the North Pole. But if you throw it at an angle, if you throw it at an angle at high enough speed, it'll actually go into an orbit, right? But if it's coming straight up and straight back down, or just straight down from the start, that's zero angular momentum. Okay, so the lowest energy state that you can have, and the lowest suborbital on every energy level is angular momentum 0. At n equals 2, the second energy level, we can put some more electrons. And we can only, n equals 1, we can only get 2. That's it. You know, because it's got to be a straight pop up from the North Pole, L equals 0, and then, you know, up and a down, clockwise and a counterclockwise. That's it too. But energy level 2, we can have either L equals 0 or L equals 1. And this is actually in units of Planck's constant, h. So L equals 0 means no angular momentum. L equals 1 means actually a unit of h. In fact, for electrons, it's h over 2. Now, the other thing that happens when you do have angular momentum, a magnetic field can show and reveal further definition by splitting the angular momentum states into 3 spatial suborbitals. Okay, and so those suborbitals. So if you put some carbon or anything else into a magnetic field, you'll see some of the spectral lines split. You know, so for the hydrogen that we were looking at from n equals 3 down to n equals 2, you could cause that to split into 3 very closely spaced spectral lines if you have a strong magnetic field. And I've done that in the lab. So 3 suborbitals, okay? And then each suborbital has 2 electron states, a plus and a minus, an up and a down, clockwise and a counterclockwise. And so the 8 orbital states are available. There they are. There's 8 more, okay, at n equals 2. There's 2 for L equals 0, and then there's 6 more for L equals 1, split into 3 suborbitals. So you can think of it as being split into X orientation, Y orientation, and Z orientation. All right, so 8, but carbon only needs 4 up there. You know, carbon is 6 and 6. 6 neutrons, 6 protons in the nucleus, 6 electrons for a neutral carbon. And students, atoms in general like to be, tend to be neutral, electrically neutral. And that is because if something's missing an electron, it'll want to draw in any electron that comes near it. If it's an ion, it's missing, if it's positive, it's missing an electron, and it'll try to draw one in. If it's got an electron, an extra electron bound to the nucleus, it'll tend to lose it. Okay? It wants to be neutral because if it's neutral, it's not going to attract a whole lot of notice. But if it's negative or positive, it's going to get into more interactions through the Coulomb interactions. So carbon at n equals 2, it's just going to have 4 of them up there. So we better erase a couple of these babies. Okay, 4 of them are unfilled. Let's cut those 4. Okay, and then the 4 that are out here in the outermost energy level, those are called valence electrons. All right? And they are used for bonding. Now we're going to talk about bonding and how electrons achieve bonding. And it's not just carbon, it's oxygen, it's other elements in the periodic table, except for the very far right, the last stack in the periodic table, which are the noble gases. So this, if you look at this carbon here, it wants to have 4 more in the outer shell, in the outer n=2 shell. It hasn't got it. So it can borrow those from other elements, and when it borrows them, it bonds. So carbon bonding to hydrogen. Yeah, they can do that. CH4. But 4 hydrogens. It'll borrow those electrons from the hydrogen and form a bond. So let's talk about that. Let's talk about bonding. So here's the main thing you want to remember. Other elements react chemically to either gain or lose electrons, and carbon can do either. Carbon's one of those elements. It can lose 4 or can gain 4. It likes to lose 4. It likes to gain 4, either one. It's kind of halfway, half full. It'll gain or lose in order to attain a filled outermost energy level, as in the noble gases. Now, you may be saying to yourself, Dr. B, what are the noble gases? The noble gases are helium, neon, I think the next one is argon. The extreme right-hand column of the periodic table. So make a note of it. Noble gases, the stack all the way on the right, the rightmost column on the periodic table. And the reason that they're noble is they don't make chemical compounds. Helium doesn't really form chemical compounds unless you ultra force it. I mean, you could force it to make a compound, but it won't be a very stable compound. Okay? They don't make compounds, and the reason for that is their outermost energy level is filled. It doesn't want to gain or lose anything. Right? So, now here's the electron theory. The electron theory of chemical bonding states that only the electrons in the outermost orbitals of an atom are involved in chemical reactions. So for carbon, that's the 4 outermost babies, the valence electrons. Okay? And the reason for that is they're not as tightly bound. The ones down there at n=1, ooh, baby, they're in close, and the carbon is not going to let them go very quickly. But the outer ones, yeah, they're kind of loosey-goosey out there, relatively speaking. So they're the ones that are going to, be, the interactions of those outer electrons are going to control the various chemical properties, how things bond. Does sodium bond to carbon? Does it bond to aluminum? What is it? What does it bind with? How and what proportions? Does sodium bond with 1 silicon or 2 silicons or 2 calciums and 2 sodiums and 1 silicon? How does it work? All that's controlled by the outermost electrons. Now, this stack is the upper left column, actually the upper left 2 columns of the periodic table. The leftmost column, starting with hydrogen, and then lithium, and look at this, hydrogen 1.01. Why is that? Why isn't hydrogen exactly 1.00 flat? Because there are some isotopes of hydrogen. One of them is called deuterium. It's the hydrogen that you find in heavy water. So that brings that up above 1.00. Same with these guys. Anyway, these things here in this first stack, hydrogen, lithium, and sodium, they've got 1 electron. They've just barely parked 1 electron on their outermost energy shell, their outermost energy level. So hydrogen has got 1 electron, n=1, but n=1 wants to have 2, and it gets it, but not with hydrogen. It gets it with helium. All right? Lithium, same. Lithium is lithium-3. So it's got 3 protons in the nucleus, and it wants to have 3 electrons. But that third electron is the only one up there when n equals 2. And because of that, it's easy to strip out. And that's why, you have lithium batteries for your phone. Hopefully it doesn't start on fire like those other ones did. But lithium-ion batteries, yeah, that's why lithium is valuable for that, because of that lone electron. Sodium, down here. Sodium, it's pretty pathetic. Sodium's one of these items that you can steal its outer electron for a fare thee well. Magnesium, beryllium, they're a little bit less pokey. They have 2. Magnesium and beryllium, they're in the second column. 2 valence electrons, 2, right? Now, hydrogen doesn't have somebody right next to it, because if you get another electron, that means you've got the only energy level filled, and that means you're noble gas. So noble gas is all the way on the other side. So at the top of the periodic table, the next element to the right of hydrogen is helium, and it's all the way over in the noble gases. But for the second row here, lithium, you got to go way the heck over to the other side to get to neon. That's the next noble gas. We'll take a look at that in a second. So let's take a look at lithium. Lithium-7. And here's a picture of lithium-7. All right. Now, to fill the outermost energy level, you've got to, take care of the ground state, n equals 1. Okay, there's 2 electrons, a right side up and an upside down, an up and a down. All right. And then you've got this second energy level, first excited state, n equals 2. And all you've got out here is this baby. All right. So to fill the outermost energy level, you could strip that outer one, and then all you'd have is n equals 1, but it would be full. Or you could add 7 more. So if you could ionize a lithium to lithium minus 7, 7x. Oh boy. Hold on a second. God love you, students. I have to. Okay. All right, so either strip the outer electron or add 7 more. So the normal way for lithium to have a filled outer energy level is to strip 1. Okay, so that's the moral of the story. Okay, and that's called oxidation. I'll have to get to that later. All right, now I want to show you, talk about these 2 babies. All right, lithium is up here. Let's talk about sodium. That's over here, right below it. And let's talk about chlorine. Chlorine way over here. All right. Now, this is kind of an interesting situation. Sodium is a metal. So go ahead and write that down. Sodium, it's a metal. It is solid. It's not very, it's not as tough as iron or anything like that, or magnesium, but it's a metal. But did you know that sodium, metallic sodium, if you expose it to air, specifically the moisture in air, it'll explode. And when I was in high school, my old chemistry teacher, Dr. Cooper, was working with some solid sodium. I don't know what he was doing in the storeroom, in the back room behind the chemistry labs, and he accidentally exposed it to air and blew up. Blew him across the room, and he was okay. A tough old guy, tough old bird, as they say. But they called the cops, and we had to evacuate the school. No, they didn't call the cops. They called the fire department. You know, the fire trucks coming in and we evacuate the whole school. It's quite a day. So sodium, explosive when exposed to air. Chlorine. Chlorine is a gas at room temperature. Chlorine. Did you know that chlorine is a weapon of mass destruction? Yeah, it's a poison gas. They used it in World War II. They killed millions, well, not millions, but a lot of people, a lot of the soldiers. And the ones that they didn't kill, they harmed for life. It just rips your lungs apart, apparently. Poison gas, weapon of mass destruction. But Na and Cl, each on its own, sounds horrible, right? One explodes, one's a poison gas. But together, they bond together. What do they form? Salt. Ordinary table salt. The salt of the earth. We have to have it. We have to consume so much salt or we'll perish. Isn't that weird? Two things that are, like will kill you, but when you put them together in a bond, they're healthy for you. Sarah.
Sodium chloride is table salt.
Right. Any other kind of salt? Are you thinking sea salt?
Yeah.
Sea salt is going to be sodium chloride, but it's going to have other stuff in there like other salts. Because the sea it's not just water and NaCl. It's got do you know there's gold in seawater? It's hard to extract, but there's gold in seawater. If you could extract it from the entire ocean, you'd have a lot of gold. But it's just hard to extract. So there's other things in there that will make salts. I think that's why stuff that's good for you, like magnesium. A magnesium salt might be in there. I don't know exactly what's in sea salt. It's a good question. I should look it up. But I think that's what the story is, if you do look it up. So let's take a look at the valence electrons for sodium. Now here's the sodium atom up here, all right? And it's got, in n equals 1, first energy level, it's got 2 electrons. Now I don't have the up and down arrows, but you could. The n equals 2 energy level, it's got 8, all right? It's got the 2, L equals 0, and it's got the 6, L equals 1. And then out here on the third energy level, all by himself, is that one little n equals 3 electron. Right now, that's the valence electron. That's the one that can be stolen. If you're sodium, that's how you bind, by either sharing that one or getting it stolen. And chlorine steals it, because chlorine can really pull it. Now, if you do take that away, you have a sodium ion that has got 11 protons. You haven't done anything to the nucleus down here. You've got 11 protons, but you've only got 8 electrons, so your net is a net positive. So this is sodium, a positive sodium ion, Na+. And this is what binds to chlorine. Chlorine gets this guy, and chlorine becomes a negative ion. And then those two, bind together. And that's where you get an ionic bond. Anyways, the point is that the outer levels of this sodium ion are like the outer electron levels of a neutral neon. Okay, so here's the neon atom, 10 and 10. 10 protons, 10 neutrons. And then 2 n equals 1s, 8 n equals 3, 8 in the n equals 2 over here, right? So that's what a neutral neon atom is going to look like. And that's what these energy levels look like, all right? So the way that compounds bind together, they try to either empty that outer one or fill the outer one. Now, sodium it's going to be, like lithium, it's going to be easiest to steal that outer electron. All right. Now, let's take a look at carbon and oxygen. We've already talked about this a little bit. All right. Now, carbon right here, it's one of those elements that can go 4 units over to the right, and if it does, if it gets 4 electrons, it'll have a neon-like outer shell, if it gains 4. All right? And oxygen only needs 2. Right? So oxygen needs 2. Carbon, to get a neon-like outer shell, needs 4. Okay? Now, the other way that carbon can get an outer shell filled is by losing electrons. Now let's skip back 4 spaces. Instead of 4 spaces to the right, let's go 4 spaces to the left. Here we go. Right? There's 1, 2, 3 to lithium, and then 1 more all the way over here to helium. All right, so carbon, let me go back to that. All right. 1, 2 to beryllium, 3 to lithium, and 4 all the way over here to helium. So if carbon loses 4, okay, it'll have a helium-like outer shell. 2 electrons, and that's it. If it gains 4, it'll be like a neon outer shell. 2 plus 8, ding. And so it likes to, and carbon can do either one. All right, now let's take a look at carbon. Here's carbon 12, n equals 1, n equals 2. We got 2 electrons down here, and n equals 1. And we got 4 up here, and n equals 2. Now, we already know about that. Let's take a look at oxygen. 2 down in n equals 1. And oxygen's a little bit bigger. It's got 6 up there in n equals 2. Now, the easiest thing for carbon is to get 2 more. And that'll bring it up to 2 and 8. Ding. But carbon has to lose 4 or gain 4. Now, if it loses 4 and it shares them with the oxygen will be happy, but it's still got 2 more that it's got to get rid of. Right? So what happens is this. You take 2 oxygens, all right, and you say bye-bye to the outer 4, all right, and you give them, you say, all right, bye-bye, and you give those to the 2 oxygens. And now look at what you got, all right? Your carbon, you've stripped out 4, and now you're down to n equals 1. You got 2 down there, happy as a clam. And then your oxygen on the left, your oxygen on the right, each one of those has got another 2. So its outer level is got 8 total. All right, happy as a clam. So the carbon, go ahead and make a note of this. The carbon in this configuration, it is bound to the oxygens. And it's feeling, man, I feel like helium, baby. Those outer electrons. And then oxygen's over here. Oh, forget about helium. I'm feeling like neon. Its outer electron orbitals are feeling like neon. So those 2 babies, and those are the noble gases. That's what we call that stuff. Carbon dioxide. That is why carbon dioxide binds that way. Right? That's what we got. We're doing good. So let's look at some of these bonding methods. Okay? And there's 3 types. Ionic, we already mentioned this. Sodium chloride. The sodium loses the electron. The fancy word is transferred, but I like to use the word stolen. The sodium that gets its pocket picked of that little old electron out there in n equals 3, and it goes to the chlorine. And the chlorine's happy as a clam because now it's completed its outer shell. All right. Now, the other kind of bonding is called covalent. This is the one where we fulfill what we call octets, shells of 8. And covalent bonding is typically between non-metallic elements on the periodic table, right-hand side usually. Then we have something called metallic bonds, and these are not different elements usually, but a bunch of iron atoms bonded together in a metallic lattice. The outer electrons move freely through the metal, kind of like an electron gas, and that effectively bonds the atoms together. And the interesting thing about metallic bonds, not only do they conduct electricity because of those free electrons, those valence electrons just blazing all over the place like a cloud of electrons, but they also conduct heat as well, pretty efficiently. Copper is a good conductor of heat. But not everything is a good conductor of heat. Not all metals. But pure metals usually are. And just so you know, the metallic bonds are really difficult to model mathematically. Now, I want to show you the difference between ionic and covalent. And make a note up here in number 3. Covalent bonding is a purely quantum effect. Ionic bonding is something that Coulomb could have predicted if he'd known anything about electrons, because anything positive will be attracted and bound possibly to something that's negative. So if you ionize one atom and you give that electron over to another atom, you'll have a positive and a negative, and they'll attract. That's what sodium and chlorine do, right? But the wave functions tell you how covalent bonds work. Now, if you have two L=0 wave functions, like for hydrogen, if the curved area here, this reddish area, shows the intensity or the amplitude of the electron wave. Now, this is the L=0, so it doesn't have any directionality. It's just as the distance increases from the center, the intensity or the amplitude goes down for these waves. So they don't really have wiggles in them. They just diminish to 0 from the center of the atom. And here's two atoms. Here's one atom here where my cursor is. This first peak on the left. And then the second peak, I've moved my cursor over here to the right. This peak on the right, that's the location of two atoms. Now, if they're far away, the amplitude of the wave function is down here at sea level. See, now right above where my cursor is here, right above the word symmetric, the wave function amplitude is pretty small there, right? So that's flat water, right? That's sea level. But over here, by the atom, you have a big, strong wave. And so in de Broglie's interpretation, when the wave has a high amplitude, the probability of finding the electron there is high. That's the probabilistic interpretation of quantum mechanics. So where that wave function is a big amplitude, you're going to find the electron probably. Where it's low amplitude over here, in between, nah, not really. You're probably not going to ever find it there. All right? Now that means that we've got two separate atoms. Now, if you bring them a little closer, things start to change. All right? If you get them closer, you start to get overlap. Write down the word overlap. Now, you still got those two peaks, but now the left side of one of them is overlapping the right side of the other one, and just like waves that overlap in the ocean, when you have high amplitude interacting with high amplitude, you get a rogue wave, get constructive interference, and right here in the middle between the two peaks, you don't get to sea level. You're still way up there. Okay? It's not the highest amplitude, but it's still significant. And what that means is that right there where my cursor is, the probability of finding the electron is high. Now up here in the upper diagram, above the word symmetric in the middle, the amplitude of the wave functions is really low. So you're not going to find any electron there. But over here, and here's the square of the wave function. That's what the probability is actually proportional to the square of the wave function. Just like the energy is proportional to the square of the amplitude of the electric field. Yep. The square of the amplitude, the probability is proportional to the square of this baby. And this is where the bonding happens, right here in the middle. Okay? So where that square is big, ding, that's where you're going to tend to find the electron. It's a wave. So you can't localize it, but you can say to yourself, I have the best chance of finding it wherever the amplitude is high, and actually wherever the square of the amplitude is high. Okay, so that's the bonding, right? And that's constructive interference. So make a note, that is constructive interference. And this is after doing a bunch of calculus and using imaginary numbers. You can jot that down if you want. We're not going to do any calculus or imaginary numbers, but we are going to mention it. Now, we're probably going to end on this note, electronegativity. All right, now you're going to need this for the homework, so let's look at it carefully. Electronegativity is basically this. If a given atom has a strong electron pulling ability, like chlorine, it's going to tend to steal from another atom that has a low stealing ability. And the quantity for that is called electronegativity. Okay? It's the comparative ability of an atom to attract a bonding or valence electron. Okay? So sodium has a relatively low electronegativity, and chlorine has a pretty high, Jessica, pretty strong electron pulling ability. And so chlorine steals the electron, becomes a negative ion. Sodium loses an electron, becomes a positive ion, and then you get an ionic bond. Now, if your electronegativity is not really far apart, then you have a covalent bond. You'll get constructive interference, and you'll get bonding that way. Okay. Now, here's a table. You can look at page 288 and around there to read about electronegativity. Let's take a look at this. Here's sodium over here, 0.9. And here's chlorine over here, 3.0. And so what you want to look at in the electronegativity table is the difference. So delta, the difference of electronegativity is 2.1. All right? Now that means that you've got an ionic bond. Now, if we get a couple elements for which delta is a little smaller, we'll just have a covalent bond. Now, we know which one we're going to look at, carbon and oxygen. There they are. Difference is just 1.0. Okay, so that's a covalent bond. All right? Now, I want you to jot this table down quickly. This is how you can tell whether you're going to have a covalent bond, ionic bond, or maybe a polar covalence. It's almost ionic, but it's still covalent. Right? One of them is a little bit stronger than the other, but covalent is 0.5 or less. All right, now you're going to need this for homework. And in fact, what I'm going to do for homework, I'm going to give you this question. With which element can magnesium form an ionic bond? Now that was going to be a clicker question, but I'll give it for your homework. So let's be dismissed. It's 1:20. I'll see you Thursday. You'll have homework a little bit later this afternoon. You're dismissed.